All right, we'll get started. First off, there's some questions about the midterm, so why don't we talk about that first, and then we can move into the lecture. Yep.
Yeah, so Professor, I just wanted to ask that will there be MCQ questions or numerical questions?
I don't know. So I haven't written the midterm. I've never taught this course before, so I don't have a midterm from last year either. So I'm not sure what I'll do exactly. I would like to I'd like to test your knowledge of the concepts, and so numerical doesn't really work that well with it. So I suspect that there probably wouldn't be a lot of numerical questions, if any. Maybe there might be a few. If there are, I'll give you like a chart, like a multiplication chart or something like that, so you can do it by hand. You can also bring a calculator if you want.
Okay,
as well.
Professor, in the last lecture you told that there will be 1 to 2 questions that will check our ability.
To check which, sorry?
In the last lecture you told that there will be 1 to 2 questions that they will check our ability, that how will we know that? In the last lecture you told that.
Sorry, I'm not catching the word you're saying.
I'm saying that there will be 1 to 2 questions that
Yeah.
will be checking our ability, that how well we know the concepts, right?
Correct, yes, yeah.
So what's going to be that in that questions?
Okay, so all the questions on the exam, not just one or two, will try to test your ability to understand the concepts. That's what the exam will be about. Yeah. And then I don't know any, I can't tell you what a specific question is on the exam.
Okay, so if we want to practice that, how shall we do that?
Yeah, so to practice, the main thing, my advice always is just spend time trying to understand everything. And if there's things that you're not clear about, try to rewatch the lectures. You can ask ChatGPT, you can research a bit or whatever. Just try to get a solid understanding of what's going on. If you can understand it, you should be able to answer the questions. Yeah. So I wouldn't spend a lot of time doing practice questions or things like that, because there's no way to really practice. There's nothing to practice. It's just a question of understanding everything. Yeah.
Okay, so if you upload your notes to ChatGPT and just write a prompt to give the questions, will that help?
Perhaps. So if you want to see what a sample question is, you could ask it to generate an exam for you. My questions might be similar, they might be completely different. I can't guarantee that, yeah. But I would only use that as a way to sort of test whether you understood things. But the most important thing is I would just spend 100% of my time just trying to understand, not trying to predict what the exam questions will be or what they'll look like. I would just spend all my time just trying to focus on understanding the concepts. Yeah.
And Professor, what about the assignment that you are saying that we have to get the use case of?
Yeah, so the assignments, I kind of slipped too late. It got too close to the exam now, so maybe I'll put the assignment out next week, but I'll have it due after reading week. I know you probably all have a lot of exams around now, but yeah, I'll make it due maybe 2 weeks after reading week or something like that. Yeah. Yeah. Yeah, so I guess I didn't explicitly say about the midterm, just about the final, but for the midterm as well, you're allowed a cheat sheet.
And it's one-sided or?
So double-sided is fine. So a standard piece of paper, double-sided. Yeah, you can handwrite it, you can print it out with a computer or whatever you want. Also, bring a pencil. Do the exam in pencil, and if there's a Scantron form, you'll do that in pencil as well. Yeah.
How is going to be concept questions? I mean, in the part of the polynomials, how is going to be conceptual questions in that?
I'm not sure. So I might give examples and ask questions about it, or I just want to try somehow to make sure that you understand what was said in class. But like I say, because I haven't given an exam before in this course, I'm not exactly sure how I'm going to design it. Yeah, something for me to figure out next week.
Will it last the entire lecture, or will there be a lecture after?
Yeah, thanks. It will only be 90 minutes. So there are some people who have accessibility considerations that give them longer time. So if anyone has that and they want like whatever they're allowed, just come to me, and then you can either write in the room, stay here and write in your allotted time. That's why it's going to be 90 minutes. Or you can go to the disabilities office and write it there. But I need to know that ahead of time so I can get a copy to them there. And because that student, let's say that like at 90 minutes, no one's done. If I give you more time, I would have to somehow give them more time, and that's not possible. So it's going to be strictly 90 minutes. Yeah. Okay, so the material, yeah, it will cover everything including today. Today, there's only one thing I want to teach you. It may not take the whole lecture. I hope it doesn't. So when we're done, we'll talk about these polynomial commitments called KZG. And so that will be the last thing that will be on the exam. And we won't go on to the next stuff today. We'll just stop there.
So basically just all the stuff you've seen.
But it will be everything that you've seen, including today. Yeah. Other questions? Okay, so let me, just for the sake, because some people might not watch the video and they might just look at the notes, I'll just, okay, so it covers everything, including this lecture. You can have a cheat sheet, 1 page. You can have a calculator, but I will try to design the exam in such a way that you don't need it. But it might save you time, like instead of looking values up in tables, you could just compute them. 90 minutes. Bring a pencil. So do the exam in pencil. If I can get it into a multiple choice format, I will do that. In that case, what will happen is you'll just give me back the Scantron, and then you can actually keep the exam. And then in that case, if you want to figure out what your mark is, I'll just tell you what the right answers are, so you can look at your exam that you kept, and you can figure out. We'll take up the exam in class, but I'll. So I don't know, this course, like, I don't know if I can get it 100% multiple choice, but we'll see. Yeah, I think that's basically it. Other questions about it? Okay. Okay, so for today we're going to talk about polynomial commitments. It's something that we sort of briefly talked about at the end of last class, but we'll kind of go through it from scratch. Okay, so what's a polynomial commitment? It's going to be a commitment function like we've seen. And instead of a message, we're going to have a polynomial. Okay. Now we're going to, first off, notice that a polynomial is a message. You can write out a polynomial any way you want and just say that that's a message. So you can use any of the commitment schemes that we've seen, Peterson or Feldman commitments, to commit to the polynomial anyways, okay? So we don't need a special commitment function for a polynomial necessarily, but generally when we talk about polynomial commitments, there's going to be one extra feature that it has that's specific to polynomials, okay? So this is sort of what its properties will be. So let's start with the properties that we've already seen for normal commitments. So there were two properties. One is binding. Okay, so we don't want to say given C equals the commitment to a polynomial, it should be infeasible to find a different polynomial, call it polynomial prime, not equal to polynomial, to reveal. Second property is hiding. Hiding we may or may not care about. So when we do ultimately these proofs where I'm going to prove to you that a computation was done right, sometimes I'm doing it in a mode where I'm just trying to prove to you that it was done correctly to save you the work of having to do it for yourself. I'm not hiding anything, there's no secrets, there's no privacy. In that case, I don't care if my commitment is hiding or not. Doesn't have to hide anything, and it just needs to be binding. There's another setting where I'm mixing secrets in. So I'm giving you a proof, but I'm also mixing secrets in. Then I need the polynomial commitment scheme to be hiding. Okay? So hiding is optional. Not optional, it's just, it depends on the use case. Okay, so it depends on use case. So sometimes we use the term SNARKs. So remember, these are the proofs that we're going to be building. And then when we have secrets involved, we call them ZK SNARKs. So SNARKs are just for efficiency. And we don't need hiding. And ZK SNARKs have privacy. So they mix secrets in. So there's secret inputs. In this one, there's, if you want to think of it as a function and you're proving that you know the inputs that will produce an output of the function, in this setting, all the inputs are known. So the person you're giving the SNARK to, they could just do the computation themselves. The only reason they want the SNARK from you is just because it takes them too long to do the computation. But in ZK SNARKs, there are secret inputs. And so the reason why they can't just do it themselves is because they don't have all the inputs to do it. So here, and if you want to keep them secret, then you need hiding. Okay. The operations that we can do with a commitment are, we can commit we can reveal. So to reveal, what I'm giving you is a copy of the polynomial and a copy of the commitment, and you're basically just going to say true or false that this commitment C is a commitment to this polynomial. And the way you do it is actually just by recommitting to it. So you say, is the value I was given, is that the same as if I committed to the polynomial I was given? So I was given the polynomial, I was given the commitment, I'm going to commit to that polynomial and make sure I get the same value out. So there's no special, this looks a little different than if you've seen encryption or decryption. So decryption, it's sort of like you apply a key and you get the message back. Here, this is like very basic. It's you have to have a copy of the message itself, and you have to have a copy of the commitment, and you're just going to re-execute it to see whether it matches or not. Okay? We will never reveal. Okay, so this exists. You can do it. You will never see it again in this course. Okay, what we're going to do instead is we're going to do, let's see if I can have a good term for it. I'll call it a selective reveal. So there's lots of terms that you'll see. Some people will say like a selective open. Some people will say open at a point. Some people will call it an evaluation. Okay, so what we're going to do here is I'm going to, you can think of this less as an operation and more kind of like a protocol, like between the prover and the verifier, but it will ultimately end up being an operation for the specific polynomial commitment scheme we're looking at. So what's going to happen is you're going to say, if you were to execute this committed polynomial at x, you would get y. Okay, but the person doesn't have the polynomial. Okay. So I'm going to do it kind of like a more of a protocol, because I think it's a little easier to think of it this way. So we have a prover and a verifier. And so what the prover is going to do is they're going to send x, they're going to send y, and they're going to send c, the commitment to the polynomial, not the polynomial itself. Okay, they're only going to send c. Okay, and then the verifier will say, is it true that the polynomial that's committed to in C evaluated at x gives you y. So if I open up the polynomial at x, I will get the value y, even though I don't see the polynomial itself. I only see a commitment to the polynomial itself. Okay, so this will say true if y equals p of x for the commitment, for C equals the commit of P. Okay, so forget about the notation. It's basically, I'm just going to give you a commitment to the polynomial, and I'm going to say that the value of this polynomial at 5 is 10. And then I'm going to convince you of that fact. Okay, so instead of revealing the entire polynomial, I can reveal selected points along the polynomial. Okay, so that's what we're going to use. We're not going to ever reveal the whole polynomial. We're just going to reveal the evaluation of the polynomial at specific points. This is specific to a polynomial. So commit and reveal are just general things. Any message, if you're playing rock, paper, scissors, whatever, you can use it. This has to do with polynomials. Okay, so that's why it's a polynomial commitment scheme at this point, is because it has this selective reveal property that has something to do with polynomials. That's what makes it a polynomial commitment as opposed to a normal commitment. Okay, questions about this before we build it? Okay. There's one other thing I forgot. Let me sneak it in here. Probably actually the most important thing for this class is we want the commitment to be succinct as well. Okay, so succinct means that the size of C is small. What do we mean by small? Well, there's different definitions of what small means before people will say it's succinct. So technically, succinct means kind of like sublinear. So it's less than linear in the size of C. What we're going to see in this class is constant. Okay, so you can think about it as constant, but technically if someone came along and said, I have a polynomial commitment scheme and the size of it is logarithmic in the size of the polynomial, that would also satisfy this succinct definition. Okay, so constant is sufficient for it to be succinct, but it's not strictly necessary for it to be succinct. So I'm just going to pencil this in as constant size. And I'll put this class here just to note that you may see things that are a bit longer than that. The other thing I didn't mention is, so here when I send the X and the Y and I send the commitment, I sometimes will have to send some other things that kind of prove that this is opened up correctly, okay? So I'm going to note that as pi. We'll see exactly what that is in a second, but it's kind of like the proof that this is done right. And we're also going to assume that this is succinct. Okay? So if I want to open a polynomial up, you have a constant size commitment to the polynomial, and now I want to open it at a specific point. I want that also to be succinct as well. So it's also going to be constant size in this class.
So the width would be the proof.
Sorry, I didn't.
This would be the proof or the
I just couldn't hear the first part of your question.
the witness will be the proof, right? Or
What do you mean by witness?
the if that we don't want to change.
Okay, so this, the witness in this case would be the P, the polynomial itself. So I'm not telling you, I'm just saying you have a commitment to the polynomial. I'm not showing you the raw polynomial. And so the witness in this case is that. That's the secret that I'm keeping from you. I'm just giving you this information about it, not the whole polynomial. Yeah. Okay. Other questions about this? Okay. Let's see. All right. I want to take a little side quest here before we come back to the polynomial commitments. And I want to talk about something that we didn't really talk about before. Let's say that I commit to the message A. And let's say I also have a commitment to the message B. Let's say I multiply these two commitment values together. Okay? What do I get as a response? Okay? So let's reason about this for the simplest commitment we saw, which is a Feldman commitment. Okay? So what's a commitment to A if we're doing a Feldman commitment? Does anyone remember? So Feldman commitments, I want to commit to the message A. What does it look like? So let's remind ourselves. Yeah, exactly. Yeah. So it's just going to be G to the A itself. Yeah. Sorry, I just wanted to pull back the Feldman commitment just so you could see it. Okay. So remember, a Feldman commitment, a commitment to the message is G to the power of that message itself. Okay. Okay, so let's just do this line by line though. So I'm going to pencil this in. So this is going to be G to the A, and this is going to be G to the B. Can I simplify this somehow or reduce it? Okay, so I get G to the A plus B. And what's G to the A plus B in terms of a commitment? Well, that's the same as the commitment to A plus B. If I commit to A plus B, it's just G to whatever I commit to, which is A plus B. Okay? So if I have two commitments, A and B, and I multiply them together, then I can get a commitment of the sum of those two commitments. Okay? So in other words, what I can do is I can compute additions even if I just have commitments. So I'm giving commitments to values and I want to add them together under commitment. I can do that. Multiplication is the operation I'll use. Okay. Do I need to see A or B in order to do this? No. Okay, I just need the commitment to A, the commitment to B. I multiply them together. It will give me a commitment to A plus B. Okay. So we call this a homomorphic operation. Okay, and so Feldman commitments, we say they're homomorphic with respect to addition. So they're additively homomorphic because if I have a commitment to A and B, I can compute the commitment to A plus B, even though I don't know what A is and even though I don't know what B is. Okay. You can, as homework, check a Peterson commitment. And the only difference is you're going to have some H's to the R's, but you can check and see that it will also hold for that as well. Okay. So I'll do this homomorphisms. All right, so we have commit to A times the commit to B equals the commit to A plus B. Okay, and so this is called addition. And Peterson has this. Feldman has this. The polynomial commitment scheme we'll look at is called KZG. It also has it. We won't use it, but it's there if you need it. Okay, what about multiplication? So what I want to see is if I have a commitment to A, I do some operation. I'm just going to write a weird symbol for, I don't know what this operation is. And I have a commitment to B. And somehow if I'm able to do this operation on the two, I'm going to end up with the commitment to A times B. Okay? So the first thing you might notice is that there's nothing probably that jumps out to you that would work. So if I have G to the A and I have G to the B, how do I commit to G to the AB? So I want to go from G to the A and G to the B, and I want to end up with G to the A times B. Okay, so you can see if I add them together, it's not going to do that. If I multiply them together, it's not going to do that. Exponentiation, if I do G to the A raised to the power of G to the B, it doesn't do it. But we're getting kind of close. If I could do G to the A to the B, right, then I would get G to the AB, right? The problem is I don't know B. I just know G to the B. And in fact, I would have to solve a discrete log to learn what B is from G to the B, okay? So it looks like I'm probably not going to be able to do this, okay? So in fact, as far as we know, there is no way of doing this, okay? So this is not possible. For all of these Peterson, Feldman, and KZG. Okay. If you were able to do this, let's say you designed a commitment scheme that's not one of these three, and it was able to do an additive operation and a multiplicative operation, then you could actually do any operation possible. So if we go all the way back to the first lecture, we said if you just have a multiplication gate and an addition gate in a circuit, you can combine them all and you can compute anything that you can compute. Okay? So if I was able to do both addition and multiplication, then I could actually do anything. I could turn any operation that I wanted to do into just a sequence of a bunch of multiplications and additions, and then I'd be able to do it. Okay, this is very interesting. People have thought really hard about, can we design commitment schemes or encryption schemes where both addition and multiplication are possible. It was like in the 70s, it might have been maybe in the 80s, where the people who made the RSA crypto system, which also has, it actually has the second, RSA has this second homomorphism, but it doesn't have the first. But they said it would be amazing if we could do both. If we could do both, then we could basically compute any operation under encryption. You just get an encryption of all the inputs, and then you put it through a circuit, and then you get an encryption of the output. People thought it was impossible. They worked on it for decades. But then in the late 2000s, someone solved it. So they came up with an encryption scheme that can do both. We call it a fully homomorphic encryption scheme, so you'll sometimes hear that term. So if you can do both, we call it fully homomorphic. And it was a big breakthrough. And the problem with the schemes is that they're pretty inefficient. So you can do them in theory, but they're not really like at the point of being production ready. Whereas this ZK SNARK stuff that I'm showing you is at that case. But the people who are into this space, into zero knowledge proofs, are also into fully homomorphic encryption. So they have lots of like work on trying to make it more efficient and use cases and building hardware and software libraries for it and stuff. So the two are like pretty tightly related, but anyways. Okay, so we can't do multiplication. Now, there are two things that we can do that are not as powerful as multiplication, but they are something. They're something more than nothing. Okay? So the first thing that we can do is, we'll call it scalar multiplication. So in this case, I'm going to have a commitment to the value A, and I'm going to have a second value B, but I'm not going to have a commitment to it. I'm going to have the raw value. I'm going to have the true value of B. Okay? And in that case, so in other words, I have an unknown value and I have a known value. If I take the commitment of A and raise it to the power of B, then I do get a commitment to A times B. Okay? So sometimes we say you can multiply by a constant. What we mean by a constant here is like an unencrypted value or a not committed value. All right, so this is the one kind of multiplication that we can do, but I need to know one of the two values. I don't have to know both of them. I just have to know, obviously if I know both of them, I can just directly compute a commitment to A times B. Okay, then the third thing that we can do is we can do a check multiplication. So if I give you a commitment to A, I give you a commitment to B, and I also give you a commitment to A times B, and I tell you that this commitment is actually A times B. Okay? So you couldn't compute it yourself. If I just gave you the first two, you wouldn't be able to compute this commitment. But if I give you all three, what I can do is you can check that this is true. Okay, that this is indeed the commitment to A times B, where A is the thing that was committed to here, times the value that was committed to here. Okay? So it's not as powerful as fully homomorphic because I can't just compute it myself. But if someone gives it to me, then I'm able to check it. Okay? Now, the way that we do this is very complicated. It's actually the most complicated thing in the entire course. Okay? So it's sort of a weird thing. It doesn't always work. It only works, I'm sort of getting ahead of myself. So let me just note that here that this works on Feldman, Peterson, I'll just put PET, and KZG. And same with this. Okay, so this has some, we'll call it red tape, sort of like some restrictions on it. Okay, so this only works on some groups GQ. So we talked about setting up these GQ groups, and that's where G is when we do G to the A and G to the B. It's not going to work on every group. The main groups that we had for GQ, where I illustrated everything with the integers mod P, mod prime. So I'll write integers mod P. And as far as we know, there's no efficient way of doing this check multiplication on the integers mod P. The other setting that's very popular for GQ are elliptic curves. And you have like your normal, we'll call them normal elliptic curves. And on a normal elliptic curves, this also isn't possible. Okay? But there are special elliptic curves that have certain properties where this operation is possible. Okay? So we can't use integers mod P. If you just pick an elliptic curve at sort of random, it probably isn't going to work. But if you pick an elliptic curve that has the right properties, then this will work. Okay? Initially, this actually was an attack. So people started doing elliptic curve cryptography, and then someone said, hey, some of you are using these curves. You should know that there's this weird property, and you're able to do this kind of check. Okay? And this might break security protocols. So this is very closely related to something called the Diffie-Hellman protocol, where you're basically, Alice has G to the A, Bob has G to the B, and you're computing G to the AB as a shared secret. And so they said that, you know, the assumptions that you're relying on for that protocol, they're not going to work over these specific curves because it has this, there's this operation that you can do only on these curves, and it lets you check a multiplication. Okay, yeah. So what you're going to do is you're going to just give me 1 second and I'll write it down, and then if it's still not clear, ask me after. Yeah, okay.
Repeat the name of the protocol?
Of the protocol?
Yeah, it was some people's name.
Sorry, the KZG, or I don't know what I said.
The latest protocol, there was some author's name or some researcher's name. Just you talk about DPL?
Oh, Diffie-Hellman, sorry. Okay, sorry, yeah. So Diffie-Hellman is like the original cryptography algorithm from 78, yeah. So it's like the very first modern cryptography. It started modern cryptography kind of thing, yeah. You don't have to know what Diffie-Hellman is, by the way. I was just sort of trying to explain the history of it. Okay, so what's the name of this special property that these elliptic curves have that let you do this? It's called a bilinear pairing. Okay, so this is the special operation. Sorry, my computer's lagging. So it's called the bilinear pairing. And people realized that it was a bug, like you could use it to attack these systems, but it kind of ends up being a feature as well, because you can use it to check out that multiplications are done correctly. So we're going to use it more as a feature. And the elliptic curves, now we just say they're pairing friendly. So it means that they have a pairing associated with them. Curves that you will see Probably the most popular is called BLS 12138. That's probably the most standard curve that has this special property that's the most widely used. And there's a bunch of other ones. Sorry?
About the one used in Bitcoin.
Yeah, so Bitcoin would be over here. Yeah, so this would be SecP 256 K1. So that's Bitcoin. And then if you look at TLS or SSL connections, you'll often see something called curve 25519. And so that's also like a normal elliptic curve. So these are, yeah, they don't have that pairing operation. Yeah. Okay. All right, so it's called a bilinear pairing. All right. The way a bilinear pairing works, we can consider at two levels, well, three levels. We can just talk about what it does without understanding how it does it. That's what we'll do in this course. We can understand it fully and understand what that pairing operation is. That's something that would take 3 or 4 lectures. And you don't really need to know what it is. You can just sort of black box it. You would have to learn all about elliptic curves and things first. So I'm going to skip that. Okay, so I'm going to just show it to you without explaining how it works. In the middle, we could try to do a toy example. So I could show you how a bilinear pairing would work on the integers mod p. And notice I didn't say, I said it, I didn't write it. I said it only works on some groups. The missing word here is efficiently. So you can actually do it on these too. It's just not efficient. But what I could do is I could pick p so small that we could do it by hand, and then we could look at it. So what I'm going to do is I'm going to upload a bonus lecture that I'm not going to test you on, and it will be just a walkthrough of what a toy bilinear pairing looks like. Okay, it might help you understand it. So if you're not getting it, or you want to dive a little bit deeper, then you can watch it. But if you're comfortable with just understanding it like it's a black box sitting on the table, then you don't have to watch that lecture, and it won't be on any of the exams. Okay? Okay, so I'm going to write down, now the next thing about bilinear pairings is they look really weird. The reason they look weird is because it's not something someone wanted. It wasn't like someone designed it. They didn't sit down and say, we want an operation to look like this. Okay? It's something that happened to be there in the curve, right? It was like a weird property. So that's why it's going to look weird when you look at it. Okay? Okay, so this is what it's going to look like. It's going to say there's a function, and it takes 2 points. Let's call them g to the a and g to the b. Okay? So the idea of pairing is that you're taking 2. Okay? So I'm going to take 2 elements, and I'm going to map them to a single element. For example, g to the ab. It's not going to work quite this easy, but I have a function. It takes 2 inputs, and I'm going to map it to one group element. Okay. All right. Now these will be in some group. There's different pairing types where these groups are either the same or they're different. For BLS, they happen to be different. I think it's a lot easier to understand it just assuming that they're the same. And so in practice, they're probably going to be different groups. So it's something that you would, if you were coding this up, you'd have to learn it at that point. But for the purposes of this course, we're just going to assume that these two are the same. Okay? So they're the same group. But the output group will be completely different. Okay? So this will be a different output, or a different group entirely.
Does it mean different characters?
Pardon me?
Does it mean different characters? Or?
Yeah, so it could be like it could be completely different, and like these are numbers and this is pairs of numbers or something like that. Yeah. The size of the group will be the same, so it will still be size q, or same order. Let's give my computer a second to catch up. So different group, but same order. Okay, so we can take two GQs and we can map it to another element in GT. And this mapping is going to have certain properties. So the mapping, the symbol that we use for the mapping is E. It's just standard in the literature. And so you'll see it all over the place once you start looking at these protocols. So I'll just use the symbol E. So, but just think of E as a function that you apply to these two inputs. Okay. So the properties of it are going to be the following. There's three properties. Okay, so if I have g to the a and g to the b, and I map these, so that's E here, so E applied to g to the a and the b, and whatever the output is, I get some group in GT, that's the output. I can take that and I can raise it to another power called C. Okay, this will be the same as if I map G. Let me just. I'm going to change this to a different generator. They can be the same, but they don't have to strictly be the same. So I'll call this H just to show that it works. Okay, if I map just G and H first, and then I raise it to the power of A, B, and C, so A, B, and C, I get the same element. Okay, so those will map to the exact same place. Okay, and generally from this, you can see that you can kind of move the exponent inside and outside of this operation, and it won't change the end result. Okay, so that's the first property. Again, nobody asked for this. It was just something that the curves happen to have, and that's why it looks like sort of kind of weird. Okay. Let me actually. I'm going to restate this a little bit better. I think it might make it clearer. So I'll say G to the A, G to the B to the C equals E to the G to the, let's say, D, H to the E, all to the F.
It's getting confusing between the E and the C there.
Okay, thanks. I'll, yeah, okay. I won't use it beyond this symbol, or this equation, okay? If, and only if, A, B, C equals D, E, F, okay? So whatever A times B times C is, you can redistribute that here. And so you can have three numbers here. And if the product of these three numbers is the same as the product of these numbers, then it's going to give you the same results. Okay? All right, so this, yeah.
Sorry, on the left-hand side, the E is the mapping function, and on the right-hand side, the B is an exponent.
Correct, yeah.
But it's
Okay.
not the same E.
Okay, thank you. Let me change it then. That's a good point. Let me do this instead. I'll do, let's do X, Y, Z. Okay?
You have to write Z.
Sorry?
Z.
Just because
Z is missing.
Yeah, thank you. Okay, good? Okay. Now, we're not going to use it in its full generality. So what we'll do is, remember we wanted to check whether a commitment to A and a commitment to B is the same as a commitment to AB. So the way that we're going to use this is we're going to say, I have a commitment to A and I have a commitment to B. Okay, and let me, sorry, I'm going to write it out in a little more detail so that. So I'm going to have a commitment to A and a commitment to B. And what I'm going to check is that the same as my commitment to AB? And then I'll just have a G sitting here, okay? We're going to see why this works. So that's going to ask, is G to the A, G to the B, the same as G and G to the AB? Okay, so implicitly, there's an exponent here that's 1. So I can check this property. So A times B times 1 is AB. 1 times A times B times 1 is also AB. Okay, so if these two values are the same, then this should be G to the AB. Does that make sense? Okay, so this is, I'm going to use this pairing to check whether multiplication was done correctly. Okay, the two other properties of a pairing are that it's sort of a consequence of it, but let's say that I have E times G to the H, and I multiply it by, say, E to the G Y. Let me put W because I used Y up here. Then that's going to be the same as E to the G to the HW. Okay, so when I multiply it, it's kind of like the first two operations come together and the second two operations come together.
When you did some undo up there, the Y and Z disappeared from the right-hand side.
Yeah, thanks. It's because, yeah, it's lagging. I keep doing undo, but then I'm undoing too far, kind of thing. Okay, the third property, by the way, is that if you map, if you say, okay, let me, I'll put it this way, is better. If I just say that the pairing of GG equals 1 for all values of G, I'll end up with these properties, because I'll just have like 1 to the power of stuff, and 1 to the power of something is always 1, okay? So if I just kind of set everything equal to 1, then this pairing property is going to hold. So we call that the degenerate case. It's a degenerate pairing. And so we don't allow that. So we say that E to the GG cannot equal 1 except for E to the 1, 1 itself. Okay? And 1 here, you can also think of like as more generally the identity element. So sometimes these things aren't integers, they're points or things like that. So 1 is like the identity when we're talking about integers, but for other kinds of things, you know, you might not have the number 1, it might not be the thing. So more generally, it'll be the identity element. Okay, and let me, fix this, I should say, except for G equals 1. Yeah.
What are not equal? The other ones are properties. I mean, this looks like you're forcing it to create a mean. In which way you're looking at these are properties of any E, and for the property G and E of G and G is not identity. That's the property of it.
So, yeah, you can think of it, I don't know if it's a property or an assertion about it, but it just is what it is. It's just basically, okay, the property is that it shouldn't be a degenerate pairing, and the main degenerate pairing would be one that looks like this. Yeah.
The number 2 doesn't read like, I mean, it looks like multiplication implies something.
Yeah, so it's kind of like a commutative kind of property, but it's a little bit different in terms of how it works. we won't use it anyways.
Yeah, but can you say again what it says?
Oh, it just says that if you have the pairing and the first two elements are the same and the second two elements are different and you multiply them outside the pairing, then you'll get G to the HW. So the different ones will multiply and the one that's the same will stay the
So
same.
it's equal, not implies.
Oh, sorry, yes. Yeah, thank you. Yeah. Okay, and of everything that we'll use of this, we're only going to use this property here. So this is the only one that will show up in what we're doing. So it will give us a way of checking a multiplication between two commitments. And we're not going to use it for anything else. And in fact, of all the homomorphic stuff we talked about, I think actually we might use the scalar multiplication. I can't, we'll know in 15 minutes, but this is I think the only thing that we use actually of the whole homomorphic stuff.
So if E is a mathematical function, given these two will provide something. Like it's a big
Yep, so you can think of it as a function, it takes two inputs and produces one output. So it maps two inputs from GQ to one element from GT. But it has a kind of collision property where when these exponents look a certain way, then they kind of collide. Okay, if you're comfortable with what's in the green box and you don't want to dig deeper, then that's fine. Then you can understand everything in the class with just what's in the green box. If you want to dig deeper into these three properties, I'll do that bonus lecture and I'll show you an example using the same integers mod p that we've been using all along. And then you'll see these three properties in action. And yeah. Okay, so I'm going to move on from pairings unless if there's other questions. Okay, and the only time we'll use this also you're going to see before the end of class. Okay, so now I'm going to go back to polynomial commitments. And I'll say that there's two constructions that are used most often. There's more than two, but two are pretty famous constructions. One of them is called KZG. And so we'll do that in this class. And the only restriction or constraint we have is that we need a pairing-friendly curve. And if we have that, then we can do KZG, because we're going to use that bilinear pairing operation. Okay. There's a second one called Fry. Fry has some advantages over KZG, and it has some disadvantages. Fry is only based on hash functions. Doesn't use anything other than a hash function. Because it's only based on hash functions, it is post-quantum. So a quantum computer won't break it. Whereas a quantum computer will break KZG. So this sounds better already. So why don't we just switch? Why don't we just throw away KZG and just use Fry? The answer is that Fry is kind of big. Okay, so it's a lot bigger. KZG is very small. And Fry it's not constant anymore. It's sort of logarithmic, and it's kind of like a big logarithmic as well. Okay, so it's technically succinct, so it's going to be way smaller, but it's going to be like a large succinct. Okay, so in practice, if we care about things really, really small, KZG is better. Okay, KZG also has a weird assumption we're going to call a trusted setup. And Fry does not have that assumption either. So it has a transparent setup. Okay. So Fry is more or less strictly better than KZG, but except for efficiency. So if you didn't care about the size of anything or the amount of time that it took, you might as well use Fry because you don't, the setup is there's no trust in it, it's post-quantum, et cetera, and so the reason that we prefer KZG is just efficiency, mainly, okay? It's also simpler to understand, so that's why I'm going to show you KZG. Fry's very, like, weird to understand, yeah. So in this case, we'll say no, so transparent is jargon that's used, so that's why I used it, but what it means is no trusted setup. Yeah, thanks. And what is a trusted setup? You don't know that yet, but you'll know that in 5 minutes, what it means. Yeah. Okay, other questions? Okay, all right, so I'm going to show you KZG. And we kind of penciled it in before, but I'll redo what we did before. Okay, first thing I want to do is I want to remind you of something we talked about last class, which is, let's say Alice is thinking about some polynomial. Sorry, I'm just going to try and draw this a little better. Bob is thinking about a polynomial, and he thinks he's thinking about the same polynomial as Alice, but they're not exactly sure. Okay. And they want to know whether they're thinking about the same polynomial or not. It's sufficient to just choose one random point. Okay, so we'll say tau is a random point. It's important that it's random, but beyond that, it can be any point that's random. And what Alice will do is just send p of tau. So they'll only look at what the polynomial is at this one point. And Bob will also see whether p of tau, his polynomial, is equal to the p of tau that he got from Alice. Okay, and if they're the same, then he's going to say it's probably the same polynomial. I'm 99.999999999% sure. Okay, and that's called Schwartz-Zippel lemma. Okay, so just a reminder of that. We're going to use that fact for this. Okay, so I need a commit operation. And now I'm going to commit to a polynomial. And so what I'm going to do is I'm going to make it look like a Feldman commitment at first. And I'm going to stick my polynomial where I would normally stick the message. So I have a coefficient times, plus the next coefficient times x, plus the next coefficient times x squared, plus the next coefficient times x cubed, and then I can just keep going. Okay, and as always, we're always working mod p. Okay, why can't I just do this? Why can't I commit to this? Well, I don't know what value to put in the square. Okay, there's no value there yet. Okay, I have the numbers, I have all the coefficients, but I need to put a value into the square itself. Okay. So the idea is to commit to this polynomial, what we're going to do is we're going to pick a random value tau, and we're going to evaluate the commitment at that value tau. Okay, so we're just going to have whatever that value is at tau, and that's what we're going to commit to instead. We're not going to commit to the whole polynomial, we're only going to commit to the value at tau. And we're going to say that that commits to the whole polynomial. Okay? So can I just can I replace a true commitment to the whole polynomial with just the commitment at one single random point? The answer is I can, because different polynomials will overwhelmingly have different points at tau. Okay? So I can get away with it. And this is what's going to make it succinct. Right? My commitment is going to be succinct because I'm taking a whole bunch of coefficients of a polynomial that's really, really long, maybe 10,000 or 10 million coefficients long, and I'm collapsing it down to just what is that polynomial at this value tau. Yeah.
If you were to take tau as 0, would that make it more likely? Because you're basically removing all of the...
Yeah, so if 0 would be kind of a deficient, like degenerate example. Yeah, yeah. Yeah, so generally we would restrict, a lot of times when we pick numbers, we exclude things like 0 from them. Yeah, so it's, what we want is we want everything up here to be closed under multiplication. And so, yeah, that's, you want values, yeah. Actually 0, that actually doesn't exclude 0 from consideration, but probably we're not going to pick 0 anyways. Yeah, okay. All right, so what I'm going to do is I'm going to put tau in. Okay. And so what I'm really doing is I'm just committing to my polynomial evaluated at tau. Whatever that value is. Okay. Now the problem I'm going to have is tau needs to be a random point. If I know what tau is, if I know it's 10, I can create two polynomials that cross at 10, even though they're different polynomials. Okay? If I create two polynomials that cross at the value tau, and they're different, then if I ever want to open this up, I have a choice. I can open it to the first polynomial or the second polynomial. That's going to break what property of commitments? It's going to break the binding property. Okay? So this would work in theory, but it would have to be a random value of tau that no one knows. If someone knew it, then they could break, otherwise it breaks binding. Okay, so what I want to do is I want to compute this value, g to the c0 plus all of this stuff. I'm going to compute it using a random tau, and I'm going to not know what tau is. Is that possible? Can I compute this exponent if I don't know what tau is? Not directly, right? Yeah, so it looks like no, right? There's no way I can possibly compute what this exponent is, unless if I know the value of tau, right? But if I know the value of tau, then it is not breaking. Okay, so this is where the trusted setup comes into. Okay. So someone, we'll talk about that later, someone is going to pick the value tau. Okay? They're not going to tell anyone, it's going to be a secret, and then they're going to delete it. Okay? And so now one person knows tau, but they promise that they're going to delete it, and they're not going to remember it. Okay? So that solves the problem of somebody has the ability to know tau. Okay? But how am I able to, for my custom polynomial, where I have my favorite values of C1 to C3, how am I able to use this tau that someone else created? I could give them my polynomial, and I could say, give me back my polynomial at tau, because you know tau. Okay? That could be one way that it works. But what they can do is something a little different. They can give me helper values that would let me commit to my polynomial of choice and compute this equation without knowing what tau is. Okay? So what are the helper values? So I'm going to tell you, and then we'll talk about why they actually help. Okay? The helper values you're going to get are g, which you already know. You're going to get g to the tau. You're going to get g to the tau squared. You're going to get g to the tau cubed. I'm going to just put in brackets just so that you know it's g to the tau squared as opposed to g to the tau squared. So it's g to the tau cubed, g to the tau to the 4, and we'll keep going. There'll be some upper limit to it, but it might be 10,000 or 1,000,000 or something like that. Okay. So I have 2 questions about this. Again, this maybe looks weird. It is weird, but we'll think about it. First off, just as a sanity check, if you give me all these values, can I figure out what tau is? How? So tau's supposed to be a secret that no one knows. If these values, say, get published, say online someone publishes all of these values, can I figure out what tau is? Why or why not? If I look at this value, do I know what tau is? Why not?
The log problem?
Okay, so a discrete log problem. So I can't pull out these tau values because I would have to solve discrete log values. Okay, so now if you have tau and tau squared and tau cubed, maybe because you know 3 powers of tau, you could do something a little easier than a discrete log. And so the exact assumption that we write down is slightly different. But for this class, I'm just going to say that you can't recover tau because of the discrete log problem. And then the second question I have is, does this actually help? These are helper values to help me compute this. Do these values actually help me compute this? Okay, so let's try it and see. All right, can anyone see a way that if I have this here, I'm going to give it a name. So the name that we call this is a SRS, which stands for a structured reference string. And the idea here is that someone's going to choose tau. They're going to compute these helper values. They're going to publish them. So they're going to make them public. And then at the very end, they're going to delete tau. And they're going to promise that they didn't write it down, they don't remember it, they have no idea what tau is. Okay? All right. Now, let's just make sure that this actually helps us, and then once we see that it helps us, I'll circle back to like why you would believe that someone would actually do this. Okay, so if I have these values here, can I compute what I need to compute here? So I can do it, that's the hint. Okay, but can you see how? How can I commit to g to the c0 plus c1 tau plus c2 tau squared? I don't know what tau is, but I do have g, I have g to the tau, and I have g to the tau squared and g to the tau cubed.
Would you have to take the values and put the exponents of your equation?
Okay, perfect. All right, so what I'm going to do is I'm going to take the first SRS. Yeah, so let's just walk through. Okay, this is... I upgraded my operating system, and now this stuff isn't working. Okay, so I'm going to take G from my SRS, or G, I just know G anyways, and I can raise it to the power of C0, and you can see I'm going to get G to the C0. Okay? Okay, let's do the next one. What's the operation? How do I get C1 to the tau? How do I get plus C1 to the tau here? Can I do it with the second element of my SRS? Okay, so I'm going to take that G to the tau. I'm going to do multiplication between these two elements, and I'm going to do exponentiation to the coefficient. Why does that work? Well, that's going to give me G to the C0 times G to the tau C1, and that's going to give me G to the C0 plus C1 tau. Okay. Then I can keep going. I can take G to the tau squared. I can raise it to my next coefficient. Then I'm going to get G to the C2 tau squared. And then that's going to add a C2 to the tau squared here. And then I'm going to just keep going until I'm done, until I have enough. Okay, so I'm going to need, my SRS has to be as big as the polynomial I want to commit to. So if I want to commit to something of degree 1,000, I need my SRS to be 1,000. Why would you trust this? Okay, why would you trust that someone would generate this and throw it away? So one thing that we won't talk about is you can do a protocol where you can have 10 people generate 10 of these, and you can combine them. So the combined SRS is the combination of all 10 people. And as long as one of them deletes tau, then nobody will know what tau is. Okay? So in practice, that's how we do it. So that's what a trusted setup looks like in practice, is we get a big group of people. They all generate an SRS. You have to do some proofs to prove that you didn't mess up the values, like these are actually the proper values. There's techniques for that we won't get into. Then everyone will combine them, and then we'll end up with one SRS. Everyone will promise to delete tau, and even if everybody doesn't delete tau and lies about it except for one honest person, then the whole thing is secure. Okay? So there's a blockchain called Ethereum. So it's like for cryptocurrencies and things like that. They did one of these trusted setups, and they had, I think, maybe 10,000 people around the world that contributed to this. Okay, so as long as one of those people, one of those persons actually deleted tau, then it's safe.
Did you reuse this SRS, or would it be like a one-time?
Yeah, so that's a great question. So can we reuse it? And that's such a good question that I'm going to put it here. So sometimes we call this a universal trusted setup, which means exactly that you can reuse it. There are other zero-knowledge systems that do not have that property. So the most famous like SNARK is called Gross 16. And with Gross 16, you also have a trusted setup. But every person who wants to do a SNARK, or once you fix the computation you want to do a SNARK about it, you have to do a trusted setup. If you change the computation, you have to redo a trusted setup. So one of the nice things about Planck, because it uses KZG, is that one person does a trusted setup once. 3 years ago, Ethereum did it, and now everyone can use it, and you can change the circuit that you're doing and reuse it. Yeah. So the trusted setup is a weird assumption. We don't like it in security, but at the same time, because it's universal and because it can be a multi-party computation amongst lots of people, it's a much more palatable kind of thing. Yeah.
Can we ensure the order of the elements in the SRS?
Yeah. Yeah. So somebody, when I say they're going to prove that it's structured correctly, they're going to prove that this is tau squared, this is tau cubed, according to like whatever order. Normally you would start with the lowest to highest, but
SRS has a tool beside all of them.
Yeah, so SRS would also have a proof that it was generated correctly, yeah, which we're skipping. Okay, questions about this? Okay, so if I can do a trusted setup, then I'm able to commit to a polynomial at tau, even though I have no idea what tau is. Okay, so I was able to compute g to the p tau. Tau is some random point. Everyone's picking a random point as well. I could emphasize that. So tau at random. Right? And if you combine a bunch of random points, the point is random. And even if some people aren't picking them randomly, but one person picks it randomly, then the whole thing will be random. So I was able to compute p to tau for my polynomial, even though I didn't know tau. Okay? And so this is the commitment to the polynomial as far as we're concerned. Okay? So the next thing that we want to do is we want to open the commitment at a point. But let's take a 10-minute break, and then we'll come back and we'll talk about how to do this. Okay, we'll wrap this up. All right. One thing I was going to mention at some point, I might as well mention it now. When we commit, we end up with kind of like a Feldman commitment, except for the message is now a polynomial at tau as opposed to an arbitrary message. Remember, Feldman commitments weren't hiding. They were binding only. You still can't pull this out without solving a discrete log. But if I have a guess at what I think is the right value, I can commit to my guess and I can see if it matches or not. So the way we solved it is we had a Peterson variant where we just added a second term with a second generator with the randomness on top. The exact same thing applies to KZG. So in KZG, there's the Feldman variant. We use that when we don't care about hiding. And that is to say we use it when we're doing SNARKs. So if we're doing SNARKs, we don't need hiding. Then we're going to use the Feldman commit of KZG. And if we need ZK SNARKs, we need hiding. Then we're going to add this extra term on the end. And then now it looks more like a Peterson commitment, and that's going to be a hiding variant. Okay. In this class, to keep things simple, we're not going to do the hiding variant of it. So we'll just concentrate on the Feldman. We'll try to understand it. We'll see how it goes all the way through Planck. And then maybe at the very end, I'll mention, by the way, if you want to do ZK SNARKs with Planck, these are the two changes that you have to make. The first one is you have to add the randomizers here, and then there's a second change that you have to make that I'll get to eventually. Okay, so now what we want to do is we want to open the commitment at a certain point, x, y. And before we do that, I'm going to simplify it. And I'm going to assume that I'm going to open the commitment at a root. So what's a root of a polynomial? That's where the polynomial crosses the x-axis, okay? So it's going to have a value 0. It is an xy value, it just has a value 0 here. Sometimes I mix this up myself. Yeah, sorry, the y value is 0, thank you, yeah. Yeah, sorry, so it's the x coordinate where the y value crosses 0, where the line crosses 0. Okay, and once we're able to do this, then we'll use that to build a protocol to do x, y. Okay. I'll just move down here. All right, so I'm going to open at root y. Okay, and I'm going to describe it like a protocol. So Alice here is the prover. She knows the polynomial. And Bob we call the verifier. Sometimes we call it like Peggy and Victor for prover and verifier, but I already penciled it in Alice and Bob, so I'll keep it. Okay, so Alice knows her polynomial. She's thinking about some polynomial. She's not going to tell Bob what her polynomial is, A, because it has a bunch of secrets, or just because it's too big. I'd have to send, remember, if I want to tell you my polynomial, I have to send you, 10,000 coefficients so that you can come up with the same polynomial, okay? So I don't want to tell you my polynomial. Instead, what I'm going to tell you is a commitment to my polynomial, okay? So I'm going to use the word K for commitment. We've been using C, but C we're going to start using for other things, so I'll just use a capital K. I'll put P here just as a commitment to the polynomial. I'll draw it so it sort of looks like a polynomial here. And it's going to be a commitment to P. And remember, it's effectively a commitment to P at tau. Okay, so Bob knows KP. All right, then what Alice will do is at some point she's going to come along and say, you know what, there's this point on the polynomial, and it's, just did it backwards again. It's a root of the polynomial. And in other words, it's x0 is a point on this polynomial. Okay, and now I want to prove that. I have to send some proof or some evidence that that's the case, okay? So that's what I'm missing here. I'll write it as pi, and that's the kind of like the proof that this is correct. Okay. Let's say I have a polynomial, and I put it in root form. What does that mean? Does anyone remember? Okay, so it's going to be x minus the roots, but I'll draw it as a square instead of an x. Etc. Let's say I take this polynomial and I divide it by this minus x, where x is what I'm claiming is the root. Okay? So that I'm claiming x, I'm saying this is the root, and so this is the claimed root. Okay? So just, this is p of x is the top, and then here I have this. What happens if I do this division and x is a root of polynomial p?
Cancels with the terms.
Okay, so this is going to cancel out with one of the, wherever the root is in the polynomial, okay? And even if I can't fully factor p into roots, it will cancel out wherever the root is itself, okay? The result of this is a polynomial, okay? So I'm going to get a polynomial out. I'll call it q for quotient. And this will be a polynomial. What if I'm lying? X is not a root of my polynomial. Okay, so I take what my polynomial actually is, I divide it by this minus x. Okay, what's going to happen? Will I get, I'll compute some value for q. It will be the division here. Is it going to be a polynomial? It will not be a polynomial. Okay, so that's the function. So if I divide by this and it's not actually a root, it's going to be an uneven division. It's not going to evenly divide. And I'm going to end up with something called a rational function. Okay? So if Alice lies about x, q will not be a polynomial. If it's not a polynomial, will I be able to use KZG to commit to it? So you might have to stare at this a bit to convince yourself of the case, but I won't be able to. Okay, there's no way I can commit because I'm going to have things on the bottom, and I would need like negative taus in order to do that. I don't have it. I only have positive values of tau. Okay, so I'm not going to be able to commit. Okay, so what's the proof? Yeah.
Here we have the polynomial y of x, and the root is like the root on the denominator is also the x that we said is its root.
Yeah, yeah. So this, just let me pencil in what I think you're saying, then tell me if you're right. But if this cancels this term, then that means whatever the root is here was the same value x here.
Also, the other roots are also the same x.
Oh, sorry, yeah. So this was actually another question that someone asked that was confusing. These are all completely different roots. So polynomials will have like 10 different roots, yeah? And so what I'm saying is that x is one of these roots. Yeah, is that clear now? Yeah, thanks for asking that, yeah. So you'll still have, so q will have all the roots that didn't divide off, and you'll just divide off that one, yeah. Okay, and the degree of q will be one less and blah, 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 but we don't really need that property. Okay, so if A lies about x, you will not be able to commit. Okay, so the proof that Alice will send to Bob is just the commitment to q. Okay, so it's going to commit to the value of q, and it's going to send that to Bob as the proof. Okay. Now, what Bob needs to do is he has to make sure, because I could just make up a completely new polynomial for q that isn't actually the division of these two things. Okay, so right now I've sent a commitment to polynomial p. I've said there's a root at x, and my proof is a commitment to a second polynomial q. But what I need to check is that q actually equals this divided by this. Okay, so I want to know, is it constructed correctly or not? Okay, all right. So Alice will send to Bob KP. Alice will send to Bob an assertion of x is a root. And then Alice will send to Bob a commitment to the value q. Okay? And what Bob needs to do at this point is he has to know, okay, is q actually equal to p over something minus x, tau in this case, because it's because p and q are, but anyways, we'll just describe this as a polynomial. Is this actually the same or not? Okay. Now, importantly, Bob has to check this equation out, but he doesn't have p or q. He only has commitments to p and q. Okay. Can he check whether p divided by this equals q if he only has commitments to p and q? He can create this polynomial himself because there's no secret values in it. It's x, which is public value. Okay. Is he able to check this out if you only have commitments? And so the answer is we want to use the homomorphic property of commitments. Okay. We have addition and we have the ability to check multiplication, not compute a multiplication. This is a division, right? So what we need to do first, it's sort of a small trivial change, but we're going to make this a multiplication instead. How am I going to do it? I'm just going to move this over to the other side. So the question I'm gonna ask instead is this polynomial times q equal to p. Okay, I don't have the polynomials themselves. What I have instead is I have a q, commitment to q. I have a commitment to p. So these are commitments. Can I make a commitment to this value? Can I commit? First off, what is this value here? Is this a polynomial? It is a polynomial. Okay, so this is a polynomial. It's the polynomial C0 plus C1 would be -1 times x. Okay, so that's the value itself. Am I able to commit to this if I wanted to? I can do it, right? I just need tau. I'm going to fill it in for tau here. I don't know tau, but what I can do is I can take g to the tau. So I'll take g to the, sorry, I think I confused myself. Just give me a second. Yeah, sorry, I need to rewrite this. Okay, so this as a polynomial, I got mixed up because x here is a constant. So the first coefficient k0 is -x, and then I have a coefficient of 1 times square. Okay, so what I'll do is I'll do g to the power of -x, and I'll take my g to the tau, and I can raise it to the power of 1, which is the coefficient here. Okay, so now I'm going to get a commitment to this little bit here. Okay, so now I have commitments to all 3 bits. I want to check, does the commitment of k times kq equal kp? Okay, how am I going to do this check? So it's multiplication, but what do I need to do a check of multiplication? Pairing, yeah. So I'm going to use the pairing in order to do this check itself. Okay. So the check will be, I'm going to check the pairing of the commitment to P. I'll do it with G. And I'm going to ask myself, is that the same as the pairing between K and, I'll give this a letter just to distinguish it. We'll call it V here. So I'll say KV and KQ. Okay. What's KP? KP is G to the P of tau. And I have G. K to the V is G to this stuff. So it's G to the tau minus x. And K to the Q is G to the Q of tau. Okay. And by pairings, what I can do is I can take the exponents and I can move them outside. So let me do that just so it's a little easier to understand. So I'm going to have GG, and I'll move the P to the tau outside. And here I can have GG, and I'll have tau minus x times Q of tau. Okay. Are these two equal? Well, they're only going to be equal if the exponents are equal. Everything else is the same. Okay. So this is only going to be equal if P to the tau equals tau to the minus x times q of tau. Okay, and that's what we were setting out to prove. P equals q times box minus x, but we're filling in the box with tau. Okay, and so if this holds, then it's true. Okay, so let me go back to the protocol because I sort of scribbled out the whole thought process, but just as a protocol, Alice sends to Bob a commitment to P. Alice tells Bob X is a root on P. Alice sends to Bob this Q value, okay? And then what Bob does very succinctly is he just checks whether the pairing between KP and G equals the pairing between KQ and KB.
So for the Q, is it also Q and tau?
Sorry, say it again. For the Q?
For KQ that Alice sends to Bob, is that the same as like
Yeah.
tau as well?
Yeah, so when Alice sends to Bob KQ, that is, when it becomes a commitment is when tau gets introduced. So tau is like, yeah, when you convert a polynomial into a commitment, all the boxes, the empty boxes get converted to taus. Yeah. Yeah. Okay, questions?
So what is Alice proving to Bob?
She's proving that X is a root. So it proves that this statement is true.
No, higher level, like the solution is correct, something like that. The solution has been encoded in the polynomial and then here, right?
I didn't get your question. You're asking like, why do I want to prove that something's a root? So we don't know yet. Yeah, no idea. I'm just teaching it to you because it's fun. No, there'll be a reason why, but nothing you've seen in this course tells you why yet. Okay, so this is great if you want to prove roots of a polynomial, but generally we don't want to prove roots. We want to prove points. Like not all points are going to be roots. Okay, so what I want to do is I want to open at an arbitrary point xy. So I think a picture might help here. I'm going to call the polynomial p tilde, just for reasons that don't matter. And what I'm trying to prove to you is that this value is on the polynomial. Okay, so I give you a commitment to this polynomial, and I'm going to prove you that this value here, with this x value and this y value, is on the polynomial. Okay? All right. Actually, I regret this. I'm going to call it P. Just I think it's easier to understand as P tilde, but I'll call it P here. Okay, so our little protocol here is Alice sends to Bob a commitment to polynomial P. Alice knows P, Bob doesn't. So Alice knows what P is. Alice says, hey, xy is on P. And this is a statement that we want to prove. Okay. Bob's going to do one little step in the middle that we'll talk about. Then what Alice will do is she'll send to Bob the same thing. She's going to send a commitment to a quotient polynomial. The quotient polynomial Alice knows, so she knows Q, but she's not telling Q, she's just telling the quotient polynomial. And then what Bob's going to do is the exact same check as before. He's going to check whether the pairing of KP and G is the same as the pairing of KQ and KV. And that's basically just checking whether that multiplication is true, if Q times V equals P. Okay, so we just have one little step in the middle. Consider a polynomial. I want to draw it here. I'll call it P tilde. So I want to draw a picture of this polynomial. What I'm going to do is I'm going to take P and I'm going to subtract a number from it. I'm going to subtract the number y, where y is the number that Alice told to Bob. Okay? Visually, what happens to that polynomial? Okay, so what I'm going to do is I'm going to slide it down by y. Okay? So I'm going to get the exact same polynomial, except for every value will be slidden down by y. Now, we wanted to prove what the point was here at xy. Where does this go in the slidden polynomial when we slide it down by y? It goes to the x-axis right here. What's the name that we give to a point that crosses the x-axis? Is a root. Okay. So what I did is I took the whole polynomial, I slid it down by y, and now instead of me proving that y is on P, what I can do is I can prove that x is a root on P tilde, which is just P subtract y. Okay, so I can take P, I can slide it down by y, I get P tilde, another polynomial. I'll prove that x is a root on that polynomial, and that will imply that xy is a point on P. Does that make sense? Okay, so and I have a protocol for proving how to open the root here. Okay, so it basically just works. The other thing that we can use is the additive homomorphic property of polynomial commitments to do the subtract y. So if I have a commitment to A and a commitment to B, and I want to subtract y, then I can just multiply in g to the y, g to the minus y, and it will create that. Okay, so let me just write it out so that you have it, and then and that's the last thing that we want to do. So what I'll do is I'll compute a polynomial commitment to p tau, and it's just going to be k to the p times g to the minus x in this case. Okay, and then I will prove x is a root on kp using what we just used before, using above. Using this protocol here. So the only thing is I'll go through this protocol, but I'll replace, instead of doing kp's, I'll replace it with kp tildes, or I'll replace it with this here. So what I can write it in with it. Basically, this is the change that's going to be made. When I do the pairing check, instead of using kp, I'm going to use kp times g to the minus x. Okay. And I'm going to ask whether that equals e to the KQ and QV. Okay, questions about this? Okay, so what we have at the end of the day, what's the sort of takeaway? Alice has a huge polynomial P. She sends a small commitment. How big is the commitment? So the commitment is just one group element, GQ. Okay. So she sends a small commitment of P to Bob. It doesn't have to be interactive either. A lot of times it might be like I post it on the web so everyone can see it. But, and then she can open any point on P for Bob with a small proof. So all she sends is this Q value. She sends a second commitment to Q. So let's say I want to open 10 points on the polynomial. I can send 10 commitments to the Qs, and then that's it. Okay. Now I should mention that there are ways of doing what's called a multi-show, where if you're opening 10 points on the same polynomial, you can do it faster than running this protocol 10 times. You can kind of batch things together. And then there's other things, if you have 10 different polynomials and you're opening them all on the same point, say I want to look at point number 5 on 10 different polynomials, I can batch those together as well. And then there's some techniques that don't really save a lot, where if you have 10 different points on 10 different polynomials, you can try and do something to do something slightly faster than just running the protocol 10 times. But for the sake of this course, we'll just assume that if you want to open more than one point, you'll just redo this polynomial for every point that you want to open.
I'm sorry, I must have been distracted for a moment.
Yeah.
Can you just restate where the G to the minus x comes from?
This part here, right?
Yeah, sorry.
So that is me sliding this down by y, and the reason it's confusing is because I made a mistake. Yeah. Thank you.
And up there.
Yes, thank you. Yeah, this is the problem of teaching a course for the first time, is I sometimes make silly mistakes. Okay, questions about this? Okay, so we've now made all the building blocks that we need for Planck, finally. Took half of the course. And of course, we'll have the midterm next week. There won't be a lecture, even though it's only 90 minutes. And then the lecture after that will take the midterm up, but then starting during that lecture at the end, we'll get into Planck itself. So the second half of the course we'll actually start building a zero knowledge proof for the first time. But anyways, this is a good milestone because we're now done all the background that we need to understand it. Okay, any questions about anything? Okay, good. Then I'll see you all next week, and good luck studying.